How many people have used Scala? How many people have used Clojure? How many people have used Lift? Okay. So my background, I've written a bunch of commercial spreadsheets, and I kind of didn't realize they were a functional programming language until many years later. I founded the Lift Web Framework project. I wrote Beginning Scala. I've been coding in Clojure for 3 years. I've been coding in Scala for going on 9. It'll be 9 years in November. I was trained as a lawyer, but I really love technology. Also, I have to hold a microphone, which is kind of weird because I always talk with my hands, and it's like, ooh. So the presentation structure, I'm going to go through some background on Scala and Clojure. I'm going to do some live coding, thoughts and questions. I always like an interactive audience, so if you have questions, don't be shy. Raise your hand, throw things at me. Let's talk. So Scala. Scala is a hybrid functional OO language. It is a language that, as far as I can tell, attempts to be all things to all people. You want something that's got Java syntax? Yeah, you can use Scala. You can write Java-ish code in Scala. You want OO? Yeah, Scala's got great OO. You want functional constructs? Yeah, Scala's got tons of those. You want a powerful type system? Yeah, Scala's got that. In fact, I kind of refer to the type system as a gnarly type system. And I initially did this presentation in Beijing. So I looked up the Chinese translation for gnarly, and then I translated the Chinese translation for gnarly back to English, and it is crazy, dangerous things that people do that are exhilarating, or something like that. And I think the type system in Scala is crazy, powerful, and can hurt you if you're not careful. There's also excellent interoperability between Scala and Java. Clojure is a modern Lisp and functional language. It, to a great degree, deprecates the idea of object-oriented programming and focuses more on functional programming. There are a couple of optional type systems. Some are test time, some are compile time, but you can do typing in Clojure. In fact, some of the type systems in Clojure are more expressive and more powerful than Scala's type system, and I don't know Haskell's enough. I've only done about 6 months of Haskell, but the kinds of types that you can express in both typed Clojure and prismatic schema are, I believe, more powerful than what you can express in Haskell, which is kind of cool. Clojure is the most opinionated, or second most opinionated language I've ever used. The most opinionated is Haskell. But Clojure is very opinionated about state and mutability, which is you shouldn't do it except in very isolated, well-defined places. And this differs from Scala. Scala has a lot of immutable data structures. It's got a lot of immutable constructs, val versus var, etc. But it doesn't really express an opinion on whether you should choose one or the other. And depending on what your coding style is, depending on what libraries you use, you might go one way or the other. So yeah, if you're a Scala Z kind of person, you're going to be focusing on the immutable parts of Scala. In Clojure, you have to work really hard to introduce mutability into your code. Unless you're using underlying JVM libraries, but for the most part, you don't have to do that in Clojure. Also, Clojure has better Java interop than Scala does, which is kind of surprising given that Clojure deprecates or eschews object-oriented coding. But all of the Clojure core libraries extend their counterparts, their counterpart interfaces in Java land. So all the Clojure collections are implementations of various different Java util list, Java util map, etc., whereas the Scala collections are not. And yes, if you're living entirely in Scala land, that's not really a big issue because you can do implicit conversions, to and from collections. But if you're living in interoperability land between Scala and Nashorn, which is the Java 8 JavaScript engine. And I've done some projects where Nashorn lives inside of inside of a Scala project. You really have to do a lot of work to make sure that what you're passing as parameters to Nashorn is understandable. So in Nashorn land, if you pass in something that implements Java util list, it just appears as an array in JavaScript. In Scala land, it doesn't. But if you pass a vector or a lazy sequence from Clojure into Nashorn, it just works. So, kind of at the margin, the Java interop between Clojure and other stuff in the Java ecosystem is better. Both languages compile into Java bytecode, JVM bytecode. So, you look at both languages, you look at a jar file that's produced by either compiler, the jar file is, decompilable, it's verifiable, all of those things that you expect in JVM land. Both languages can subclass Java classes. And this is actually one of the interesting things for me the first time I used Scala, which was, as I said, almost 9 years ago. I was like, okay, let me subclass some Java classes. And without any work on my part, it just worked, which I thought was really spectacular. I mean, today we take it for granted, but back then most of the JVM languages, most of the alternative JVM languages, were not really interoperable with Java in the same way that Scala was. Both languages can implement Java interfaces. So in both Scala and Clojure, you can just say, this particular thing extends something in Java land or implements something in Java land, and it just works. So you can pass stuff back and forth between Java libraries. And both Scala and Clojure have their own wrappers around some of the common Apache libraries and other stuff so that the libraries are presented to the end user or to the end developer in the style of the language, or in Scala's case, in many of the styles of the language. So the similarities between the languages, both languages support immutable data and collections. So in Scala, you have case classes. In Clojure, you typically express most of your data structures with maps. It's super easy to pass functions, blocks of code that close over local scope, even though in both cases they're compiled down into anonymous interclasses. And one of the actually interesting things about Clojure, in terms of the way that it compiles code, it knows when a variable goes out of scope and will null the variable out on the stack or on the heap. So basically, when you get to a point where you can no longer reference a variable, you're guaranteed that the variable isn't going to be retained, which is something that you have to do manually in Scala. So if you have a method in Scala that has a function that takes as its parameter something, and that function, the method continues to run, continues to loop. If you're using tail recursion or something, if you get to a point in the Scala code where that variable has gone out of scope, you still retain it on the Scala heap. You have to manually release it, and it's actually led to some issues in some of the larger Scala projects that I've seen, where you have kind of the main loop that retains variables, retains deeply nested memory structures, and retains a lot more memory than it should. Clojure does the right thing. It's kind of one of those little subtle things that the Clojure compiler writers got right. Both languages are really great for reducing complexity and for building concurrent systems. Reducing complexity has to do with the fact that you can compose a lot of the functionality in your code. And I know that the promise of OO was supposed to be composability, but I've never seen OO actually be composable, with the exception of maybe the Smalltalk libraries. Also, with immutable data structures, those lead to both concurrency and distributed systems very, very effectively. Because if you have a reference to something and you know that when you hold on to that reference, nothing is going to change out from under you. It means that the reference can be passed across threads without having to worry about synchronization, without having to worry about coordination. It also means that you can treat your concurrent system as a distributed system or your distributed system as a concurrent system. Because basically if all you're passing around is data, and you know that the data isn't going to change, you don't have to worry about back references or any of the other stuff. How many people here have ever done RMI, remote method invocation, in Java? 1, 2, 3. Okay, so not, RMI was hellish because you would pass these references across the wire, and the remote code could like go in and change values in the reference, and you'd have to do some funky stuff to have leases on objects so that the objects wouldn't be garbage collected, a whole bunch of other stuff. And it turned out to be a huge big mess. Whereas if you just pass data across and then you get responses back, which is a functional way of approaching the world, you basically have a much easier way of writing distributed systems. And finally, both languages address the expression problem. And who here knows what the expression problem is? Okay, we've got 1, 2, 3, 4. So the expression problem. How do you define data where you can extend the data without having to alter your original library, and also extend functionality in an original library without having access to the source code of the original library? So put in concrete terms, how do you add a method to a class when you don't have access to the source code of the class? And all I want to do is add a method to an Apache library. We have workarounds to this. We have, in Java, there's static methods, and you do dispatch in the static methods, and it's just a whole lot uglier than you really wish it was. So in Java, you can subclass, you can add new data to an existing type, but you cannot add new functions to an existing class. No soup for you. In Scala, you can actually do subclassing, you can add data, but you can also have implicits, or in scare quotes, type classes. And it's actually, I'll do a little bit of digression into one of my rants about Scala and implicits, which is they suck. They are way overused and lead to, among other things, the horrible compile times and a lot of the other issues that people complain about in Scala land. So implicit started off as a really simple concept, which is, okay, actually Java has implicits, but they are not user definable. So if you have a method that takes a float as a parameter and you try to pass an int to that method, the compiler will implicitly up-convert the int to a float. It won't down-convert a float to an int because you lose precision, but you're not going to lose precision if you up-convert from an int to a float. Well, you might, but putting that aside for a minute. So the Scala's original roots said, okay, rather than having this be hard-coded into the compiler, let's put some of these up conversions into the predefinition, into the predef, into the kind of library code rather than compiler code. And then there were other things that happened where it's like, oh, it'd be really useful to add a method to string. Well, let's just do an implicit conversion. If we wanted to add the to wombat method to string, let's do an implicit conversion. Let's do an up conversion to a class that has to wombat on it. And then say we can implicitly convert one thing to the other, so that you basically say, if I am looking for a method on a particular thing, I can up convert the thing into the thing with the method. And then you got the implicitly passed parameters, which is the thing that leads to fake type classes in Scala, which is, okay, here pass a parameter that will that the compiler can determine at compile time that will do the right thing given the types that I'm passing around. And then we kind of extend that idea to using the same thing as evidence that you can actually perform a particular type operation, and if you can't, get a compiler error. And then we'll extend that thing to say that if you can't provide evidence for a particular type operation, then here's a nice way of presenting the error to the end user. So, you know, we have this progression of, wow, we have this implicit hammer, let's treat every problem that we encounter as a nail. And, you know, then you have the question of how do you do implicit scope resolution. You know, you do it on companion objects, but then you have to do the whole hierarchy of companion objects because Scala supports subclassing. So if one of your companion objects, or if one of the types that you're passing has a type hierarchy, you have to check every one of the companion objects and blah, 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 blah. And you run into the hellish mess that is long compile times and huge memory utilization. But after that digression, ranting something, yes, you can basically solve the expression problem in Scala with implicits. In Clojure, you can also both subclass and also most of the data structures in Clojure are expressed as maps. And even if you define a record type in Clojure, you can extend or add fields to the record type dynamically, and they appear as additional entries in a hash map. The value of all of that is, and I actually encountered this when I was compiler writing. One of my side projects or side hobbies is to treat almost every project as an opportunity to write a new compiler. And I wrote a compiler for, I've written a couple of compilers. I wrote one in Haskell, and I realized that Haskell is a really difficult language to write compilers in for a variety of reasons. But one of the reasons is that you can't, if you have an abstract syntax tree, which is where compilers usually start, and you want to take that AST and basically transform it and enrich some of the elements in the AST as you go along, you have to add to your data definitions the fields that you're going to be using as enrichment. Whereas if you have a map, your data is your definition, or if you have records in Clojure, your data definition is a floor but not a ceiling. Whereas in Haskell, your data definitions are both a floor and a ceiling. And that leads to having to either have a bunch of optional parameters in a particular data definition, or what winds up happening in most compilers that are written in Haskell, you have 2 or 3 different large phases of compilation, and what you wind up doing is you wind up transforming the tree, or when you move from gross phase 1 to gross phase 2, you basically totally rebuild the tree using the data structures for type 2 from the data structures in type 1. In Clojure, I wound up writing a compiler that used enriched AST elements throughout most of the compilation phase, or phases, and I was also able to do it with purely immutable data structures, which in Haskell wound up being a problem because I wound up with 3 layers of state monads, which was a hellish problem. Anyway, with Clojure, after that ran, with Clojure you can use these things called protocols to add functionality to data. And you can even add functionality to existing classes, which is kind of cool. So in our Clojure example, this is actually used in the code that we'll be exploring in a minute, we can define a protocol that says convert from Scala to Clojure. And it has one function called 2c, which takes a parameter. And we say that we can extend Scala's iterator. The 2c function is this function that basically does a lazy build of a lazy sequence in Clojure. So like Haskell, Clojure has as a core data type lazy sequences. If you've ever used streams in Scala, they're particularly difficult to use. You can't basically build a stream out of a function that will return elements until it's done, or if you do, it's kind of a real bear to do. So most people use lists or vectors in Scala. Most people use fully reified data types rather than lazy sequences. Clojure has lazy sequences, and it's really easy to build them. Anyway, so what we've done here is we've basically taken a Scala iterator and converted it into a Clojure lazy sequence. The next thing that we can do is we can say, we can extend seek, or we can implement the protocol for seek, which is a sequence in Scala, by saying call the seek2 method, which takes the sequence, calls the .iterator on it, and then calls toC on that, which winds up executing this code. So Clojure will do dynamic dispatch or polymorphic dispatch, and you can add types to the polymorphic dispatch at runtime. You can add types whenever you want to add them, which is kind of cool. It means that you can do the same thing extending a string or any other, enriching any other data type, even if you don't have access to the library. So talking about that distributed and concurrent thing, both languages have easily serializable data structures. In the case of Scala, case classes are easily serializable. Lift.json is one of the more prominent libraries for being able to serialize and deserialize case classes and collections within case classes, etc. Both languages support immutable data structures, and like building a REST service, if you imagine almost everything in your program as data in, data out. In other words, I put some data in, I receive a transformed version of the data, but the original things that I passed in are not mutated. That leads to a very nice way of building both distributed and concurrent systems. So with all that ranting, let's go do some live coding. So I'm going to build a chat server, and the Clojure part of the chat server, actually let me just go into my IDE. Let me start up a couple of different windows. So Clojure has a build tool called Lineagen, which is the Clojure version of SBT, for lack of a better analogy. Lineagen allows you to define all of your operations, behaviors, build rules, etc., using a Clojure data structure rather than using Scala code, which is what SBT does. In this first window, I fired up something called Figwheel. Figwheel is the single coolest front-end development tool I've ever used. It compiles Clojure script code dynamically as you save files, pushes the changed Clojure script code to the client, so you never have to reload your client. You always get the fresh code in your client. You can also, you have a full REPL from Figwheel, so you can actually send Clojure script code to the browser, and the Clojure script code will execute in the browser as you type it on the command line, which is pretty cool. It means you can inspect your live running application in your browser using full Clojure script code. I'll show you an example in a minute. The second thing I'm going to fire up is Zinc. Zinc is a Scala compiler Scala compiler plugin for Lineagen. So it'll basically go through and continuously compile my Scala code as I update it. And the third window I'm going to open is a standard Clojure REPL. So we're compiling away, we're loading our REPL, and we have our REPL. What we've done over here is, you can't quite see that. This require command basically pulls this namespace into scope, which means that if the namespace doesn't already exist, it's read in, the Clojure code is compiled. And the next line is basically starting our web server. So we now have a live web server that we're running, and we can go over to our window, hit reload, and we have the bare bones of our application. So the first thing the thing I mentioned a little while ago is that I can type in a command here, and it executes in the browser. I don't know. The first time I saw that, I was like, holy cow, that's cool. So let's actually go. I found that if I try to do this, if I try to live code the whole application, I run out of time. So I'm just going to walk through the pieces that I'm not going to live code, and then we'll do some live coding. So this is our chat server. Can everybody see the font, or do I need to make it bigger? Everybody good? Okay, so our chat server is in Clojure, and we define a channel. Channels in Clojure are very similar to actors in Scala. You send a message to, or you send data to, send a message to a channel. Something else, somewhere else, will dequeue the message and process it. Much like you send a message to an actor, and in some other thread, in some other time space, the message will be processed. We have a function called postMessage, which takes the message parameter, calls 2C on it. So it takes and converts it into a Clojure data structure. And then we send it to our chat server. So we basically send the message to this channel. We have a series of chats, and we have a series of listeners. And then we have our the thing that actually runs our chat server, the thing that dequeues the messages from the channel. So Clojure's asynchronous channel supports something called the Go macro. Who here has done any Go programming? Nobody. One person. Okay. So Go also supports asynchronous channels. And the nice thing about Go is that if you're blocking on receiving a message, it doesn't consume any system resources. It's actually the same thing is true using the Go macro in Clojure. So with actors in Scala, you basically say, here's my message handler, and the message handler is called whenever a message is received. And the message is pattern matched. Whoa, what happened here? Eek. Are we back? Uh-oh. Helpful person? Does anybody here read Polish? Better make sure my machine doesn't sleep on me again. My computer slept for a minute, and the projector lost it. Questions? Let's talk about something that's like we don't need a screen for. No? All right. Well, I'll rant a little bit about the Go macro in Clojure. The Go macro allows you to write code that looks like it's linear, but wherever there is wherever the code could possibly block on waiting for messages from a channel, the thread is released. And then when a message is received, the computation is continued. What it means is that you never have callbacks. What it means is that you write what seems like linear code, and the macro, the Go macro, basically unwinds your code such that any place where could be blockage, the blockage doesn't occur. But when data is available, the computation continues. So it's a bunch of really nifty magic. Who here has done any Erlang programming? What language haven't you used? COBOL, okay. No discussion of COBOL today. So Erlang is also message-based, event-based, and Erlang also does very smart things with being able to release threads. And if you've taken a look at any of the Akka code or any of the core Scala actor code, there's a bunch of really gnarly stuff to basically release the message handler and then resume the message handler when a new message comes in. Being able to write your code in a much more linear fashion is really good. Clojure also compiles into, it has a JVM target, but it also has a JavaScript target. And the JavaScript target, where you have truly a single-threaded execution, being able to release the computation and then continue it at a future time is a super great thing without having to worry about callbacks. Do we have our screen savior? Somehow we lost the screen. No, it's here. So we got one of them working. Sure. Yeah, it's CSP. Yeah. Actually, I think it's stolen from the same paper that the Go CSP stuff is stolen from. Sorry, liberally borrowed from. Okay, yeah. I don't think we can move over there unless that cable is long enough. Okay, yay. Thank you. All right, so we've defined our series of chats, we define a series of listeners. Now you'll notice these things called atoms. Atoms are where you put mutable state in Clojure. So everything is immutable unless it's an atom. There are a couple of other immutable things, but they have a similar presentation. So we default to an atom with an empty vector, an atom with an empty vector. Our run loop is a Go macro, or runs inside a CSP routine. So Go is the macro that tears apart our code and does the right thing. We do pattern matching on receiving from our chat server. So what the macro is going to do is it's basically going to say, okay, this is a potential block point. So any code, when we get to this point, if there's nothing on the channel, release the thread. And when there's something on the channel, continue the computation. So in this case, we're going to pattern match on the contents of the message. And if we have an add message, we are going to take the last 40 chats. The @ sign dereferences the atom. So it says, I'm going to get the value out of this atom. Take the last 40 and send it to whoever we're adding as our listener. Then take our listeners and append the current listener, or the listener that we're trying to add, to the list. So swap is a function that takes an atom, in this case listeners, and performs a function on it. So conj is appending a value to something. So it appends the current listener, the one that we're adding, to our list. The remove message takes the listener, does the same swap. In this case, we're going to remove from our list anything that's identical to the listener. So like Scala, Clojure also uses the equal function as equality as value equality rather than reference equality. Identical is reference equality, or equals across objects in Java. And finally, if our message is a string, we're going to, for each of our listeners, send to the listener our message. And then we're going to swap out by appending appending that message to our chats. So one of the other things that we see here is do seek. By default, map and filter and all the other operations, collections operations in Clojure are lazy. Do seek is strict. So it will go through and perform the operation and not return from the function call until all of the elements in the sequence have been processed. So if you're going to do something that has a side effect, you're going to want to do it inside of do seek, because otherwise you're not guaranteed that it's going to happen. Otherwise, we do nil, and then we call ourselves and basically do recursion. So that's our loop inside of Clojure to run our chat server. Questions so far? So how do we hook that up into Scala land? So Lift has a concept of snippets. So when you rewrite HTML in Lift, you don't just send out a bunch of strings, you manipulate the DOM. So this idea is kind of new and improved in the browser with all the JavaScript frameworks, but Lift has been doing it for 8+ years now. So we have a snippet called actorize, and the render method is the default method that's called when the snippet is invoked. Let me actually open the index.html file. So in the index, we basically invoke the snippet by saying data lift actorize, and what that does is it passes the DOM element into the render method, and then whatever is returned from the render method is inserted into the DOM before the DOM is passed out over the wire. So if we go back and look at actorize, we wrap all of our stuff in a tail, and because Lift does DOM rewriting, we can actually insert a tail element into the DOM, and before the DOM is turned into a string and sent out, or turned into bytes and sent out over the wire, Lift goes through and moves everything that's in a head tag, even if it's in the body, up to the head, everything in a tail tag down just before the close body tag. So, you can basically insert scripts and a whole bunch of other stuff anywhere in your page, and they get rendered out the right way. So we build a client proxy. The client proxy is an actor that when you send a message to the actor in Scala land, the message will actually be serialized, pushed out to the browser, and this function will be called. So basically the receive function will be called in our browser code. When we shut down the actor, when the actor goes out of scope, when the page is unloaded, we basically we post our message and we remove the actor, our listener, from the set of listeners. So this is how we do our house cleaning. And our data filter says when this actor receives a message, take that message and turn it into transit code. So the folks at Cognitech who do Clojure also wrote a really, really nice cross-language data serialization protocol. So it's called Transit, or Data Serialization System. So Transit will take a whole host of different data representations and convert them into a superset of JSON and send them over the wire. So they deal with things like UUIDs, they deal with dates, all the things that you wish you could deal with in JSON, but you can't. So what we're doing is we're going to basically take the data that comes in, turn it into a transit data object before sending it over the wire. And finally, once we get our client proxy, we're going to add our listener. So you remember we had the 2C function call when our channel received a message? Well, 2C says, okay, a Scala symbol turns into a Clojure keyword. A Scala tuple, basically any product type in Scala, will turn into a vector of elements in Clojure land. So this 2-element tuple, this symbol plus a value in Scala land, will pattern match against this line in Clojure land. So, nice simple interoperability. You have two things that are semantically similar, and they just kind of get converted. Questions so far? Nope. Finally, we have another actor, and in this case, it's an actor that lives on the server that will be presented on the client as a JavaScript function. So when you call the JavaScript function with data, the data is serialized and sent to the server, and then this actor receives a message from the client, or receives a message which contains the data that was passed to the function on the client. So in this case, we're going to get a string, we're going to post the message to our listener, to our channel, but we're going to do a transit read on the message. So we're basically going to take the string that we received from the server, do a transit read, which will reify the objects into nice, fresh Clojure objects. And finally, we emit a script that says the variable send to server is whatever script will create the call to the server from the client. So what this does is this gives us two different actors. One is an actor that lives on the server and is a proxy to a function on the client, and the other one is a function on the client that is a proxy to an actor on the server. So we have now set up full two-way communication between the browser and the server without having to do any plumbing at all. Or this is the extent of our plumbing. We haven't set up REST routes, we haven't done anything else. And the very interesting thing about all this is it's purely secure. So you can't fake any of this stuff. It's all based on GUIDs, globally unique identifiers. So the plumbing within Lyft actually knows how to route an incoming AJAX request, an incoming post or a GET, based on the GUID that's associated with it, but you as a developer don't have to think about that. It's nice and safe. Okay, so we now have all of our server code. Let's go and start working on our client. So the client is based on a library called reagent, and what we're going to do here is we are going to, where did I put my little purple notebook with my notes of things that I have to do? Oh crap, no, don't, did we lose it again? Is it over there? Or? All right, do we have questions? No?
I've got one.
Yeah.
Are there any problems with cooperation between Clojure and Scala? We saw that in your example that it's easy, but are there any?
So the question is, are there any challenges, difficulties, rough edges in the operability between Clojure and Scala? And the really short answer to that is no. The slightly longer answer to that is that Scala does a bunch of stuff that is uncallable from Java. So for example, the bang operator that you use to send messages to actors is name mangled in Scala. And the names are illegal to use in Java. You can't use $sign in a method name at the Java compiler level, but not at the JVM level. It turns out that you can use those symbols correctly from Clojure. So you can actually call name mangled Scala method names from Clojure without any penalty, which is really, really sweet if you think about it. It's like, oh, okay, I can call into Scala from Clojure more easily than I can from Java. And you know, once again, at the end of the day, it's all JVM objects. And when we get the thing going again, you know, kind of the conclusion is the two languages are semantically similar. And because they're semantically similar, it doesn't really matter what you have. And so if you remember, we had the send bang function that we used to send a message. That send bang function is actually a protocol. And one of the things that I implemented against that protocol is an actor. Another thing that I implemented against that protocol is a CSP channel. So you can use the send function on the protocol to send a message to a channel, to send a message to an actor, and they just work the right way. So you actually, solve the expression problem, which is, okay, I have the send function. What am I sending to? Oh, I'm sending, I now know that I have a Scala actor or an Akka actor or a Lift actor that I want to send something to. I can extend my protocol and it will just work. Can we see it? Is anything up over there? Okay, good. Yay. All right. So, given that I have 10 minutes, I actually did a git reset hard so that the code is actually fully running. What you didn't get to see is you didn't get to see me build it up, but, hello. Yay, the chat works. If I go over here and I try to open my app over here, yay, the chat works. If I chat between the two, yay, gets updated in both. Let's take a look at the client code, quickly run through it. This is the HTML. So we basically have an H2 that says chatting. We have an unordered list with LIs, with list elements. We have an input field, and we have a button field. So how do we add behavior to those? We will go in and take a look at our Clojure code, which is right over here. So we get our chat.html template, and we do a transform. And we say insert into LIs each of our chats. So each chat that we receive will basically be inserted into the body of the LI. Because it's a collection, if there are 20 of them, we'll actually generate 20 LI elements. So, if we go back to our template here, we have one LI element, and that one is then duplicated many times within the UL, one time for each element in our chat. The next thing is we add on-click behavior to our button, and what we do is we use a sum threading macro. Sum basically says take the first value and pass it as a parameter to the second value. If the second value returns nil, return nil from the whole expression. If the second line doesn't return nil, go to the third line, continue. So it's a nice way of kind of doing what one would do with options in Scala, or it's a nice null checker. So we basically say swap ID in, which gets the old value of in and sets the new value to blank. Take the first element, swap ID returns a vector of the old value and the new value. So we only care about the old value. We do a transit write, and then we send to server. And you remember in our Scala code, we created a JavaScript function that was send to server. So that JavaScript function sends our transit encoded string out to the server, and the server actor sends that to the chat server. The chat server then adds it to the list of chats, and then rebroadcasts it out to all the listeners. So that's it for UI. In terms of receiving a message from the server, so when a message is sent to the proxy actor on the server, the receive function is called. So we do a transit read, convert it into a fully reified item. We use and we test to say, is it sequential? If it's in effect a list or a vector or whatever, we reset chat, so we set the chat atom to the value of the vector. And if it's a string, then we basically update the chat's object by appending it. When the chat's atom is updated, because the atom is referenced over here, this code is rerun and the display is updated. That's it. You don't have to have explicit callbacks or listeners or a lot of the other stuff that leads to that works well if you're doing one or two elements, but if you have 50 elements on the page and you have to like figure out which of the 50 elements are using things, it gets gnarly. And let's actually do a nice demonstration of that. So let's go over here and say div id equals wombat, and we'll go back to our client and we will say quote dot. Is it hash or dot to look up in CSS? I'm sorry? Hash, thank you. We're going to set the body of wombat to be so we update our code. So all I did was save the file. My page got updated. I didn't have to hit reload. If I do something like script alert hi. So I'm trying to do something malicious. The right thing happens because the string type is retained, and we know that we're inserting a string into the DOM element rather than creating a DOM element out of a string. So you basically get resistance to cross-site scripting and a whole bunch of other stuff for free by dealing with things as DOM elements rather than dealing with things as strings. But you can see that both elements got updated when we changed the single atom, rather than having, and I guess it's cheating a little bit because it's in the same part of the page, but if we had 5 different elements in the page that were all referring to the same atom, all of the elements would be redrawn. The other thing that's happening with the redraw is that React, which Facebook's React.js, which is what the Clojure script framework that I'm using is based on, does DOM diffing. So over here we actually rebuild a whole DOM, but it's a fake DOM rather than a real DOM. And then that DOM is compared to what the browser is displaying, and only the elements that have changed are changed in the browser. So the cost of doing an update is relatively low, even though we're doing apparently redrawing everything, but basically we're creating some data structures, and the data structures are used within React to figure out what needs to be changed to cause a real I/O event, to cause a real browser reflow. And the browser reflows and redraws are the really expensive things, whereas manipulating a couple of bytes here and there is pretty cheap. So that's our demo. Let's go back to so kind of wrap up. It's really easy to convert between Scala and Clojure types. Oh, actually, I promised to show you guys the server code. So we have a protocol called sendable, which has a single function send. And if you pass a Clojure function to sendable, sendable just applies that function to the data that you're trying to send. If you have a Scala function 1 that you pass in to sendable, if you do a send bang on that, you just apply, once again, the same semantics that you would do with a closure function. If you have a many-to-many channel, which is the actual class for the CSP channels, then you do a put on the channel. And if you have an actor, then you do, as I promised, a bang on it. And, you know, it's simple interop. And if you do something even cooler, like annotating like this, then the Clojure compiler does type coercion into lift actor. And so you're not doing a method lookup, but you're actually doing a normally fast JVM operation. So by making that one change, by basically hinting to the compiler what the type is, I've now given full Java Scala speed for a method dispatch. Both Clojure and Scala do well with distributed apps. I mean, in this case, a distributed app was just sending a string around. But the difference between sending a string around and sending a rich JSON object around or a rich Clojure object around is pretty close to 0. And the JVM really does make it easy for everybody to play together. Yeah, call a method, it's a method, you know, whatever. So they, in fact, do play well together. And I am just about out of time, but let's take some questions if you guys have them. The man of many languages.
I got a look at the SDK code. It allows to use Clojure from within the SDK project.
Yeah, actually, I used SBT Clojure on a primarily Scala project that I worked on. Unfortunately, when I was building this demo, Figwheel does not run inside of SBT Clojure. And Figwheel is like the single coolest thing that I've played with in a while. I mean, it actually, you know, it reduces development cycles really quickly, which is you save the file and then you see the changes, which also gives really good demo. There was a question behind you. The question is, do I do this in real life, or am I just doing this to get a conference slot?
No, I mean the interrupt between Clojure and Scala.
Yes. So I actually did, I spent about 6 months last year working on a project that was primarily Scala, and they ran into some problems where they needed to dynamically update logic. And basically the issue was the business people would change business rules on a pretty regular basis. Nobody here is familiar with that. I know it's a really isolated case where the business people want to change the rules on you. The client is actually in the business of updating rules for their clients in terms of processing messages. So it's not the normal pointy-haired boss thing. It was it was a legitimate business function. And one of the things that they realized, they had a cluster of about 200 machines running message processing for all this stuff. And doing a rolling update 2 or 3 or 4 times a week where they basically had to build a new WAR file or a new jar file, update the jar file, do a rolling restart, make sure that the restart was successful, you know, blah, 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 blah. That was really turned out to be a headache. And so what they wanted to do is they wanted to be able to do something where they could dynamically update code, dynamically update the business logic by, you know, doing something easy. And the easy thing that we wound up doing was writing a row to the database. You know, it's like, okay, here's a blob of data that expresses the new business logic. Being able to compile that data down into Clojure and then run that Clojure code through the Clojure compiler using eval. You can do live evaluation. You wound up getting performant JVM bytecode that interoperated with the Scala code, could call into the Scala code, could do all the things that you wanted it to do, ran, I don't know, you know, 55% of the speed of the Scala code, but, you know, close enough for business work. And the amount of resources for DevOps for doing an update went from, really, in effect, 2 people doing the rolling restarts constantly to 0 people. Other questions? Well, I really appreciate your time. I really appreciate you sitting through our own versions of rolling restarts. And I hope you have an awesome rest of your conference.